Hey friends, Dr. Borole is here. Welcome again. Today we are going to study the field effect transistor, also called as FET. Field effect transistor consists of three terminal: drain, source, and gate, denoted as D, S, and G respectively. FET is basically a voltage control device. In case of BJT, we have seen the input current gives rise to the collector current. So input is a current and output circuit is also controlled current. Whereas therefore BJT is a current control device. Whereas in FET, input is in the form of voltage and that voltage controls the output current, and therefore FET is a voltage controlled device. It is voltage controlled current source type of device. In field effect transistor, gate field effect controls the channel width and hence the drain current. What is field effect? We will see after the construction during operation. FET is a unipolar device or majority charge carrier device. We have seen in BJT the conduction takes place because of hole as well as electron, and therefore BJT is basically a bipolar device, bipolar charge carrier device. Whereas in FET, the conduction takes place only by one type of charge carriers, either electrons or hole, and therefore FET is considered to be unipolar device. There are two types of FETs: N-channel FETs, in which conduction is due to electrons in the channel, and another type is P-channel device, in which conduction is due to holes in the channel. We will see shortly what is N-channel device and how it is constructed and how P-channel device is constructed. Classification of field effect transistors. Field effect transistors are broadly classified in two groups: junction field effect transistor JFET and MOSFET, metal oxide silicon field effect transistor. Whereas metal oxide silicon field effect transistor MOSFET is a current generation device which is very popular in most of the electronic circuits or electronic devices and ICs nowadays. It virtually replaces BJTs as well as junction field effect transistors in the application. In all of the digital technology devices, including microprocessor and microcomputer, the chips are now manufactured with MOSFET as a basic building block. MOSFET types. There are here the following figure indicates the classification. Junction field effect transistor have two types: P channel and N channel JFET. Whereas MOSFET have two subtypes: enhancement type of MOSFET and depletion type of MOSFET. Under both the categories, there are P channel devices and N channel devices. Now, what are the differences and similarities between FETs and BJTs? See, one of the major differences: BJT is a bipolar device, whereas FET is a unipolar device. In FET, the current conduction takes place due to majority charge carriers, and therefore it is a majority carrier device. Whereas BJT is a bipolar device. It is simpler to fabricate FET than BJT. Since FET takes smaller space, the packaging density or integration density is extremely high compared to BJTs. The FETs have high input resistance because there is no electrical connection between the input terminal and the channel. It can be used as a symmetrical bilateral switch, means the source and gate terminal can be interchangeable. It functions as a memory device also. You will see further in the other subject of computer science, the semiconductor memories. The basic building block of the semiconductor DRAMs are the MOSFET devices. There are static RAMs and dynamic RAMs. The MOSFETs are used in fabrication of memory devices because they takes very small space, so therefore large memories can be implemented using MOSFET devices. BJT BJTs are larger in size and therefore implementation of memories using BJTs accommodate less number of memory devices or memory location on the same chip, and therefore for larger capacity semiconductor memories normally MOSFETs are used. The FET devices and MOSFET devices are less noisy compared to bipolar transistor. They exhibit no offset voltage at zero, hence makes the excellent signal choppers. These comparisons and various differences in the characteristic may be asked for 3 to 4 marks in the examinations. The main disadvantage of FET is its relatively small gain bandwidth product called GBW compared to BJT. Means the amplification gain provided by FET or MOSFET devices is less compared to BJT. Now let us see the N-channel depletion MOSFET, also called as D-MOSFET. Here we are studying the MOSFETs. Junction field effect transistors are not mentioned and removed from the syllabus, and therefore we are focusing from MOSFET onward. So it is a depletion type of MOSFET. Let us see the construction of depletion type of MOSFET. It consists of a P type of substrate, means P type of bar. In this bar, two islands of N type of material are diffused by using diffusion procedure. And similarly, some N minus type of island is diffused between the two end N plus bars here, N plus islands. So here this upper and lower N type of diffused regions, they are called drain regions and source region. Whereas the N channel, N region, which is connecting this upper and lower N type of islands, that is called as channel. So ultimately, in all total, this is a N type of semiconductor material. The electrical connections are done to it and the terminals are taken out. One terminal is called drain and another end of the N type of material, the terminal is named as source. Whereas on this N type of material bar, there is a silicon dioxide layer which is a insulator layer. The gate terminal is fabricated on the other side of the SiO2 layer and it is above the channel bar. This is in short the construction. The fourth terminal which is connection to the substrate is called as SS terminal or substrate terminal. The symbol of N-channel D-MOSFET, depletion MOSFET is shown here. Gate, drain and source terminals. The another symbol also quite popular for the same D-MOSFET is shown. So both the symbols can be alternatively used in practice. Now let us see how N-channel depletion MOSFET works. Let us consider the operation with gate to source voltage 0, means gate is shorted to source. When gate is shorted to source means nothing is connected or gate is grounded. Here in the channel it is N type of material. The upper island is also N type and lower island is also N type. Now when the electric voltage VDD is applied to the upper terminal and common or ground terminal is connected to the source terminal, the electric field is established in the channel and it attracts the electron present in N type of channel via the upper terminal. So upper terminal will attract and drains the electron to the biasing power supply VDD and therefore the upper terminal is called drain. Whereas the electrons are supplied via the lower terminal and therefore it is a source of the electrons or charge carriers and therefore the terminal name given is source. So when no gate to source voltage is applied or zero gate to source voltage is applied, the channel have full of charge carriers and when external voltage is applied VDD, these charge carriers are moving. Electrons are moving from source to drain and flowing through the outer circuit. Whereas therefore conventional current is in opposite direction. The conventional current is shown by the dotted line which is flowing from drain to source. Since the channel is fully open, the current flowing through the channel is maximum and it is denoted as ID is equal to IDSS. IDSS stands for drain saturation current when VGS is equal to 0. When VGS is 0, channel is fully available. So channel width is maximum and therefore current is maximum. Now how the depletion operation takes place, let us see. When the negative supply voltage is connected to N-channel MOSFET, here in the figure, the channel portion is replicated. Now when negative gate supply is applied, here it is N-channel shown. This is the substrate. This second part or remote part is a substrate and exactly below the SiO2 layer there is a N channel. Now gate is negative. Due to this negative supply, the electrons in the channel, they are negative particles. So negative gate supply will repel the electrons or push away the electrons towards the substrate. When the electrons are pushed away from the substrate, they are leaving behind the positive ion and they are immobile. When more and more negative supply is connected, means VGS value is more and more negative, more and more atoms are uncovered and becomes immobile positive ions. They occupy the large space exactly below the gate. And since they are immobile, they are not taking part in the conduction. Ultimately, what we observe is as gate voltage is more and more negative, the effective width of the channel is decreasing. If the channel width is decreasing, the number of electrons flow through this restricted channel are also decreasing. And obviously, if number of electrons are decreasing, then the drain current is also decreasing. So if the negative gate to source voltage applied, channel will be depleted with the charge carriers by reducing the width of the channel due to the depletion field effect of the gate supply voltage. The barrier is formed in the channel here but due to immobile ion. This is the field effect that is created by the gate to source negative supply, which restrict the channel and therefore reduces the current. Since this is a depletion effect, therefore the name of the device is depletion type of MOSFET. Since the device is made up of metal oxide semiconductor and therefore it is called as MOSFET. Let us see whatever the operation we have explained, same can be depicted from VI characteristic of N-channel MOSFET. Let us see the curve. On y-axis there is a drain current and on the x-axis see the negative side, second quadrant. Here we are decreasing the voltage from 0 to negative value, that is VGS. So when VGS is equal to 0, the full channel is available, channel width is maximum and the drain current is also maximum here, say 8 milliampere shown in this figure typically, and that is denoted as IDSS. When we go on increasing the magnitude, negative magnitude of VGS, as we have seen the channel is getting restricted and obviously therefore the current is decreasing. At a particular voltage, say pinch of voltage Vp, the gate to source voltage strength is such that the total channel is now occupied and depleted with the charge carriers. There is no charge carriers available. The channel width will be shrink to 0. No channel is exist between drain and source and therefore no current flows. And therefore this happens at a particular voltage called pinch off voltage. So pinch off voltage is nothing but it is the value of VGS at which channel totally pinches off. Means drain current cease to exist. That is called pinch off voltage. Now if you see the graph, if you see, if we apply instead of negative voltage, if you apply the positive voltage, you will see the current channel will be enhanced because when the positive voltage is applied to the gate, these electrons are getting attracted from p-type substrate and additionally attracted electrons increases the charge density in the channel. So more electrons are available when positive voltage is applied and therefore current will be increased when the drain supply is connected and therefore you will see as you go on increasing the value of VGS in positive direction, drain current further increases above IDSS linearly. These characteristics are called as transfer characteristic because drain current is in output circuit and VGS or gate to source voltage is in input circuit. So the relationship between output quantity and input quantity is therefore called transfer relationship and therefore it is called transfer characteristics. We will see here the characteristics are linear for short duration over the short portion, whereas over the entire region of the characteristic, the curve is non-linear in nature. Now let us see the another characteristic called drain characteristics. These characteristics are defined as VDS versus ID characteristic of the MOSFET. Now you will see here, if we go on increasing the value of VDS and plot the value of ID, you are getting the characteristics. Let us suppose VGS is equal to 0. When VGS is 0, channel is fully open. If you go on increasing the value of VDS now, the channel current remains constant because number of charge carriers are remains constant. So even increasing the value of VDS doesn't affect the current because number of carriers moving are constant. Therefore, we can say that current remains constant here to IDSS. We can say that the current is saturated. If VDS is reduced to smaller value, then electric field of drain supply voltage is lesser. If drain supply is lesser, it attracts lesser number of electrons from the channel. And if lesser number of electrons are drained away from the channel, the current amount of current flowing is also less. And therefore, when VDS is decreased below some certain value, this corner value, the current is decreasing. When VDS is 0, the field electric field established is 0 and therefore no charge carriers are drained from the region, the channel region, and therefore current is 0. Same thing happens at higher negative voltage at lower value of the drain current. For different value of VGS, if we plot the curve of ID versus VDS, we are getting the set of characteristic. These are called as drain characteristic because these are the relationship of drain current versus drain to source voltage. The region below which here the characteristic VGS minus 5 volt, below that you will see that the current is very small, drain current is very small, and therefore the region near x-axis at very low drain current is called as cutoff region. The region near to y-axis here is called ohmic region. That is similar to saturation region in BJT. Whereas here it is called ohmic region. Whereas the remaining region shown here where the characteristics are horizontal lines, value of VGS, if the VGS changes, the ID value is changed in this region proportionately. And therefore this region is called as linear region. And it is also called as saturation region. The saturation region here is a linear region for the MOSFET, remember. Whereas in BJT, the saturation region is the region which is ohmic region of the MOSFET or FET. So instead of having this confusing type of nomenclature, we can call this saturation region as a linear region or active region. Okay. The expression of ID is given by the relationship ID is equal to IDSS into 1 minus VGS by VP bracket square. So relationship above we have seen this VGS versus ID characteristics. Those are given by the equation ID is equal to IDSS into bracket 1 minus VGS minus VP square. This is a quadratic curve. Okay. The region of operations we have just discussed. There are three regions of operation: cutoff region, ohmic region, and saturation or linear region. In P, another type of depletion MOSFET is a P-channel depletion MOSFET. Now, what is the difference? You will see instead of N-type of channel here, it is a P-type material channel. Whereas substrate is instead of P-type, it is now N-type. The channel is formed by P-type of material and remaining thing SiO2 layer and gate is same. Whereas the gate voltage is made positive here, gate voltage is applied is positive, which depletes the channel. The symbol of P type of D-MOSFET is shown here. Both the symbols are alternately used. The enhancement type of MOSFET, now we will see. In the enhancement type of MOSFET, the construction is shown in the figure. Here, there is a p-type substrate and two island. N island here, one is drain and another N island is connected as a source. Whereas there is a SiO2 layer as usual, and on the other side the gate will be fabricated. This SiO2 layer is a insulation layer. There is no electrical connection between gate and the substrate. One thing you note that there is no channel bar present between drain and source. The symbols of N-channel enhancement MOSFET, E-MOSFET is shown here. The difference you will note here, the symbol consists of a solid bar, where here the symbol consists of a dotted bar. This indicates the channel. So in enhancement type of MOSFET, by default, there is no channel exists between drain and source when there is no voltage applied. Now operation of N-channel enhancement MOSFET. When VGS applied is 0 between gate and source, since no voltage is applied, there exists a p-type material here and here there is n-type material. So there is p-n junction here and there is p-n junction here. So it is as good as two p-n junction connected in opposite direction. So even though supply is applied between drain to source, one of the p-n junction is in reverse bias and therefore there is no flow of current. So when there is no supply voltage, there is no conducting channel exists between drain and source, and therefore drain current is 0. Now let us consider that some positive voltage is applied to the gate. What will happen? When the positive voltage is applied to the gate, this positive charge here on the gate creates or push the holes from the substrate. When the holes are pushed away, what leaves behind is an immobile ion. This total shaded portion is representing the immobile sheet of ions, that is depletion region. Due to this positive voltage to the gate, additional effect takes place. The source N type of material here, that is full of electrons present. The electrons present in this N type materials, those are free charge carriers, are attracted below the gate area, and therefore they convert the P type material here to N type of layer called inversion layer, which is the layer of free charge carriers. So larger the gate to source positive voltage, larger the width of the inversion layer formed by the electron as a charge carrier. Now we will see between drain and source terminals, there is a connection of charge carrier channel exist. Now if we apply drain to source voltage, a positive supply connected to the drain terminal with respect to source, these electrons are attracted by the supply electrical field towards the positive plate and they drain off these electrons from the drain terminal. Electrons are coming out and therefore electron current is flowing which is coming out. Therefore conventional current shown here by the dotted line, that is going inside. Larger the gate to source voltage, larger the width of the inversion layer, means channel, and therefore we can say that larger gate to source voltage enhances the channel, and obviously when channel is wider, larger, more charge carriers are present, more current is flowing as a drain current. So therefore, when VGS greater than a particular threshold voltage VT, the channel start persisting and getting enhanced, and therefore current increases with the value of VGS. If we apply the larger value of VDS greater than the knee voltage or specific voltage called pinch off voltage, the channel tapering occurs like this. Due to the reverse bias present at drain and P type of substrate, the electrons accumulation here near the drain area is reduced, whereas electron accumulation near the source area is more. And therefore, at a particular value, this channel will be pinched off or channel width will be it becomes zero when VDS reaches to the certain value called as pinch off voltage. And therefore, the electrons move from this restricted area remains constant even though the electric field of supply voltage VDS is increased, and therefore VDS don't have any effect after this value and current saturates. This current is called as constant saturation current. The VI characteristic of enhancement MOSFETs are shown here. There are two types of characteristic: transfer characteristics VGS versus ID, and drain characteristic VDS versus ID. Let us see the transfer characteristics. VGS is on x-axis and ID on y-axis. Up to certain voltage, the drain current remains zero. After that, we have seen in the operation, if we if we increase the value of VGS in positive direction, the inversion layer will be formed, and due to this inversion layer, larger number of charge carriers means channel width will be increased, and therefore more number of charge carriers are moving due to applied electrical field, and therefore larger the value of VGS, larger the current flow. Right. So these graphical characteristics can be analytically expressed by the expression ID is equal to K into VGS minus VT square. You will see it is a quadratic curve and it is a non-linear curve. If we consider over the short interval from point A to point B, it can be considered approximately linear. But overall, over the large signal condition from low voltage to high voltage, the curve is nonlinear. Whereas K is a constructional constant which depends on size and say width and length of the channel and the material constant like mobility and gate 2 or gate region capacitance COX. Whereas W by L ratio is also called as aspect ratio or dimensional constant. If we consider the drain characteristics are drain to source voltage versus ID. Let us consider the characteristic for VGS equal to 7 volt. We see that when VGS exceeds the pinch of voltage here, see the crossing of dotted line with the characteristics. If the voltage VDS is greater than this value, say around greater than 7 to 8 volt onward, the channel will be tapered and limited number of charge carriers or charge carriers passing through the shrinked area near drain are constant, and therefore drain current saturates and it remains constant. So after this dotted line shown here, VDS equal to VDS sat, the drain current saturates and remains constant. Whereas at lower value of VDS less than VDS sat here, these points. So the current is decreasing if VDS is decreasing at a given constant value of VGS. Reason being, the electric field of VDS is such that the channel length or channel width is sufficiently high, and decrease in VDS further towards zero reduces the draining electric field on the channel carriers. And therefore, if the draining electric field is less, the number of charge carriers removed from the drain are less, and therefore at lower voltage of VDS values or lower values of VDS, the current is decreasing. The region near y-axis where the drain to source voltage is low and drain current is large is called as non-saturation region or ohmic region. Whereas region near x-axis where channel is totally pinched off or no channel exists between drain and source, so no drain current flow. So drain will be cut off, and therefore this region is called as cutoff region. Whereas the region in which the drain current saturates the horizontal straight line area, this area is called as saturation region. And saturation region starts, called linear region also, it starts when VDS value is greater than VDS set. The same characteristic, single characteristic is shown. In this characteristic, the characteristic in saturation region are given by the relationship ID is equal to K into VGS minus VT square. Whereas in the sub-saturation region, this also called as triode region or non-saturation region or ohmic region, the current relationship is given by twice K into VGS minus VT into VDS minus VDS square by 2. Whereas in the ohmic region, lower portion of the characteristics here, the drain current ID is given by twice K into VGS minus VT into VDS. You have to remember these equations because derivations of this equation are beyond the scope of this subject. That may be in the next year subject, the electronic circuits. Till the time, we have to bear with it and we have to remember it. P-channel MOSFET is the another type of MOSFET. We will see here compared to N-channel enhancement MOSFET, the difference is here instead of P substrate now N substrate is used. The channel islands are of P-type material. As usual, there is no channel exist. The channel will be formed by applying the negative gate to source voltage here, which accumulates the electron from N type of substrate exactly below the gate area or gate insulation area. Whereas gate and this channel forms a parallel plate capacitor, that is gate area capacitance. So whatever the accumulation of P type of charge carriers here is called as inversion layer, and that forms a channel. Larger the positive negative gate voltage between gate and source, larger will be the width of the channel and larger will be the current flow between drain and source if drain to source voltage is applied. The symbol of P channel enhancement MOSFET is shown here. In this symbol, the current or the arrow here shown which is coming out. Whereas in this second symbol, the arrow is on the source terminal. which indicates the direction of drain to source conventional current. The characteristic of p-channel MOSFETs are similar to n-channel MOSFET, only the curve here you will see VGS will be negative, whereas in n-channel MOSFET we are applying positive VGS. The shape of the characteristic is same. The other concept, pinch off voltage, saturation region, ohmic region, semi-saturation region and cutoff regions are similarly identified in this characteristic also. Now let us see the advantages of and the limitations of MOSFETs. MOSFETs have very high input resistance. It is obvious because between gate and source there is a insulation layer, and insulation layer have high resistance, no doubt. Very low gate current. Obviously, large resistance of insulation makes current very small or zero. They have better thermal stability. They are of small size compared to BJT. They takes less space. Their dimensions are smaller compared to BJT in nanometers. The MOSFETs can be capable of operating at high frequency compared to BJT, and they are having low noise characteristics. The noise generation due to this device, due to their operation, is less compared to BJT. These are the few advantages. The limitation is high input capacitance, because between gate and source there is a SiO2 layer and it forms a parallel plate capacitance. And obviously, this capacitance reduces the maximum operating frequency. The saturation voltage is large in case of MOSFETs compared to saturation voltage of BJTs. So VC SAT is much less compared to VDS SAT, and therefore the off-state losses and on-state losses particularly in MOSFETs are more if VDS SAT is more. But nowadays technology is evolved to the new level which controls the VDS SAT to low level or even better than VC SAT of BJT. And therefore, in most of the applications, MOSFETs are virtually replacing all the BJTs and BJT circuits. Handling precautions is very important here because due to very high input impedance, the static charge will be developed across the gate and which may damage the gate area or puncture the SiO2 layer that damages the MOSFET without connecting it in the circuit. So static charge itself damages it, and therefore special precaution has to be taken. Comparison of MOSFET and BJT, whatever we have seen up till now, is listed systematically in the table. You have to go through the table. Maybe in the examination, they will ask you compare MOSFET and BJT for 4-5 marks. So accordingly, you have to write the number of points. The application of the MOSFETs. We will see MOSFET can be used as a switch like BJT. MOSFET particularly can be used as voltage variable resistance. MOSFET can be used as a constant current source like BJT. In the logic circuit, MOSFET can be used as inverter or NAND gate, and most of the logic circuits and digital circuits are nowadays using the basic building block as a MOSFET. In semiconductor memory devices, the MOSFETs are quite popular because they are having high packaging density. So larger memory sizes can be implementable with MOSFET only. The region of operation of the MOSFET, from the application point of view, the operating regions are listed here. Cutoff regions Normally, the MOSFET is operated as off switch. In saturation region, that is linear region, the MOSFET is operated as amplifier in the applications. And ohmic region, that is also called as on state region, the MOSFET is working as on switch. And these regions are shown in the graphical characteristics. So we will stop here, friends. The next part will be continued in the next session. Till then, bye bye.